Hello, and welcome to Quantum Leaps. Today, we're diving into something absolutely critical for the future of computing, keeping quantum computers on the straight and narrow. Imagine a computer so powerful, it could solve problems that are impossible today: new medicines, revolutionary materials, unbreakable codes. That's the promise of quantum computing. But there's a catch. The heart of a quantum computer, the qubit, is incredibly delicate. Think of it like trying to build a supercomputer with parts made of soap bubbles. They can pop at any moment. That's where quantum error correction, or QEC, comes in. It's like a superhero shield for our fragile qubits. You see, unlike our trusty classical bits that just flip from 0 to 1 or vice versa, qubits face more gremlins. They can have these phase flips or just lose their quantum magic, a process called decoherence. So how do we fight back? The main idea behind QEC is clever: redundancy. We don't just use one physical qubit for our information. Instead, we encode the information of a single, logical qubit into a team of many physical qubits. It's like having multiple bodyguards for one VIP. If one guard stumbles, the others can cover. Now, how do we know if an error has happened without accidentally destroying the quantum information by looking at it directly? That's where stabilizer codes come in. Think of them as secret handshakes. The encoded information has a specific pattern, and we can check for this pattern using special measurements on helper qubits. If the pattern is off, these helper qubits raise a flag. That's the error syndrome. It tells us something went wrong, and often what kind of something. Then, a classical computer, acting as a decoder, figures out the most likely error and sends instructions to fix it. The more physical qubits we use in our encoding scheme, typically, the better the protection. This is related to something called code distance. There are many types of QEC codes being developed. You might hear about the Shor code, one of the first, or the Steane code. But a lot of buzz is around surface codes. Imagine a 2D grid of qubits. They are popular because they're quite robust and seem well suited for the types of qubits we're building today, like superconducting circuits. Of course, making all this work in the real world is a massive challenge. We need physical qubits that are way more stable and less error-prone to begin with. We need to precisely control all the quantum operations. And remember that redundancy? It means we need a lot of physical qubits for even one reliable logical qubit, maybe hundreds or even thousands. Plus, we need to perform these error checks super fast. But the good news is we're making incredible progress. Scientists have already shown that these QEC codes can indeed reduce errors. We're seeing logical qubits perform better than the physical qubits they're made from. Qubit technology itself is getting better every year. There's a huge effort in designing codes that work hand in hand with the hardware and in developing super-fast decoders. The ultimate goal is fault-tolerant quantum computing, where we can correct errors faster than they appear, allowing for truly complex and lengthy calculations. Quantum error correction is the bedrock for this future. It's the unsung hero that will allow quantum computers to finally live up to their world-changing potential in medicine, materials, science, and so much more. It's a tough journey, but QEC is paving the way. Thanks for tuning into Quantum Leaps. Join us next time as we explore another fascinating facet of the quantum world.